Can you hear me? Okay, so I'd like to get started. So yesterday we talked about...
Get 15 minutes late just to give us a bit of extra time.
I'm going to tell everybody.
Shall we start?
Yeah, just say that we're going to start 15 minutes late in the afternoon.
When?
At 5:15.
Why that?
Because Neil needs to...
Oh, okay.
I drop Martha off at the...
Okay, so we're a little bit delayed, and I just heard that the delay will continue, and that this afternoon we will also have everything 15 minutes later. So in the afternoon...
Oi, shut up!
The afternoon session, Neil's talk in the afternoon will start at 5:15, and I assume the coffee will start at 5:45. Huh? Well, it's probably going to be there. Or if you come for 30, you'll have coffee, but you'll have 45 minutes for coffee. So afternoon session, 5:45. So yesterday we talked about kernels and how kernels correspond to dot products in another space. So I told you a kernel is a similarity measure. It induces a representation of the data. And I also mentioned that today I'm going to tell you that the kernel, in some sense, specifies the function class that we use for learning. And the day before yesterday, we talked about why function classes are important, or in which sense function classes are important for learning. So in learning we always have a data set, a training set, plus a function class. And then based on the training set we choose a function from that class. And how well that function will generalize. In other words, how different training and test error can be for such a function will depend not just on properties of the function itself, but on properties of the class of functions from which we choose the individual function. So it's interesting to know what is the class of functions that we are dealing with when we run a kernel algorithm. But before we get to that, I want to first revisit an algorithm that I briefly talked about yesterday, and tell you that it's actually quite interesting, and that was this trivial pattern recognition algorithm where we had two classes, two data sets. Yeah. We had two data sets, and I'm using slightly different terminology now. I will call one of the data sets uppercase X. I'll call the other one Y. So we have a data set X over here, data set Y, and yesterday we were saying we would classify a new point just by taking the mean of the dataset X, the mean of the dataset Y, and checking which of the two are closer. Now, let's introduce some notation for the mean. We can think of this as a mapping or an operator that takes as the input a dataset in the input space and produces as the output the average of the images of these data points under the feature map. So I'm going to plug each of the points of that dataset X into the feature map. Remember that one representation of the feature map was simply to say a point xi is mapped to the function k of xi with one of the arguments open. So that's just another way of writing the feature map. Yesterday we were sometimes calling it phi of xi. Think of this as phi of xi if you like. So this operator takes a dataset, maps each point into the feature space, and then takes the average of all these points in the feature space. So we can do this for both these data sets X and Y to get these two means, mu of X, mu of Y. And remember the classifier was this just looking which of the means is closer. And if we think about this, what kind of decision rule does it induce? It simply induces a decision rule which is a hyperplane, and the hyperplane is determined by this vector connecting the two means. It's orthogonal to that vector, and it intersects this line between the two means halfway in the middle. So that's our decision rule, and what I have glanced over or glossed over, I don't know what's the word, yeah. So what I have not talked about was that of course we get a problem if these two means are the same. In that case, this vector would be the zero vector, and it doesn't specify a hyperplane. So one way to deal with this would be just to say, let's assume it's not the same. But actually it turns out it's interesting to think about when it is the same. So when is it the same? Obviously, if we use the simplest case and we work it directly in input space, which means we use the trivial kernel, the kernel is just the dot product in the input space, then this would happen if and only if these two data sets have the same mean taken in the input space. Now, if we did it in a different space with a different kernel, if you think about it for a second, what if we take a polynomial kernel of degree 2? So you've seen the polynomial kernel yesterday, and we've seen that it computes all product features of order 2, the polynomial kernel of degree 2. That was the homogeneous polynomial kernel that I showed you yesterday. So it looked like this. And we can actually also construct an inhomogeneous polynomial kernel, which looks like this. And if you multiply this out, you first get a positive constant. Actually, we're not worried about that. Then you get a term in terms of this, and you get another term which has the square of this, which means that this inhomogeneous polynomial kernel computes not just features of order exactly 2, but also features of order 1. They are in this linear term, and so therefore this inhomogeneous polynomial kernel computes all features up to order 2. So now what happens if we map our data points into this feature space of the polynomial kernel of degree up to 2, and we find that the data sets have the same mean in that feature space? Any guesses? What does that mean? So it means that the data sets not only have the same empirical means, but also they have the same empirical moments of order 2, because empirical moments are just functions of these features of order 2. So that means, more generally, if we use a polynomial kernel of degree d and map 2 data sets into this higher dimensional feature space, we find that the 2 data sets have the same mean, so the same first moment in the feature space. It means that in the input space they have the all the first moments up to order d coincide. So just looking at the mean in the feature space means a lot more in the input space, depending on what kind of kernel we choose. And it turns out that if the kernel is strictly positive definite, so remember positive definiteness, and maybe I'll just write it down briefly again. Always good to see this definition again. So positive definiteness meant that for all n, for all a1 through an that are real numbers, and for all x1, xn that are in our domain, this inequality is true. And strict positive definiteness just meant that if the points are pairwise distinct, then equality is only true if all the a's are 0. So that means strict positive definite means if for all ij with I not equal j, we have xi not equal xj, and then equality implies that this vector A is identically 0, all entries are 0. Okay, so that's a slightly stricter condition. So it turns out if the kernel is strictly positive definite, then the means only coincide, or they coincide if and only if the 2 data sets are identical point by point. So that's kind of surprising. So it means, so we take these 2 data sets, we map them into the feature space, and then we compute the means in this feature space. We throw away all the rest. We don't store any of these individual things. We just store the mean. But nevertheless, the mean remembers all the points. The mean characterizes the whole data set. So why is that the case? So since this is so easy to prove, we can briefly go through the proof. And we'll prove something slightly more general, which goes as follows. So suppose we have these 2 data sets, x and y. We assume the kernel is strictly positive definite. We assume that for all I and j, all these points xi in this expansion are pairwise disjoint, and likewise in this second expansion, all the yij's are pairwise disjoint. So that's a reasonable assumption. If they were not, we would just rewrite this expansion by adjusting these coefficients. So we have two general kernel expansions. And then the claim is, if for some set of coefficients, so if for these coefficients, for non-zero coefficients, we have this kind of equality, of course we should also assume it's non-zero, otherwise it doesn't make sense. So we only take sensible expansions which have unique points and which have non-zero expansions, otherwise we just throw out the ones that had a zero. So if we have such an equality, we can write the same vector in the reproducing kernel Hilbert space in two ways. Then these two sets have to be identical. Actually, one can also prove that the coefficients then have to be identical, but we only worry about the sets. So in our case, of course, all the alpha i's are 1 over m, all the beta j's are 1 over n. And that's the only case that we want to know. We would just want to say if the means are the same, then the two sets are the same. But we prove this slightly more general thing. And we prove it as follows. So let's assume without loss of generality that there is one point, so this is by contradiction. So we want to show the two sets are the same. We want to prove by contradiction, we assume they are not the same, and if two sets are not the same, it means there's one of the two sets contains one element which is not in the other one, at least. So we assume without loss of generality this element is the one that we call x1, and we assume x1 is not in the set y. So first thing we're going to do is we will subtract the expansion over the y expansion from this thing that we had before. So we just move this to the other side. And in addition, so then we get a larger sum being equal to 0. And again, we make it a sum over pairwise distinct points. So if maybe some of the points in the set x might be identical to points in the set y. If that's the case, we would just always combine them into one and get an updated coefficient. So that coefficient could now be different. This coefficient in particular could be 0. So we remember that the coefficients we had before, all of them were non-zero. Now we bring this to the other side and make it again a sum over unique expansion kernels. Then some of the coefficients might become 0. However, we know at least one of the coefficients will not become 0 because we have assumed that the point x1 doesn't appear in the set y. So the first coefficient will not become 0. So here, this is our expansion that we get. And what we know is if we order things such that the first z here is equal to the x1 is not in the set y, then we also know that the first coefficient is equal to alpha 1, which by assumption is not 0. And all the other ones are real numbers. So we have this expansion which is 0, and we know that one of the coefficients is not 0. Next, we will take the dot product in the reproducing kernel Hilbert space of this thing with itself. That gives us this equation here. So what have we used here? We've used the fact that the kernel is reproducing. Right? If we take a dot product between this kernel and the same kernel again, of course now in the second, between this kernel and this kernel gives us this kernel here. And then we get a double sum over I and j. So we get this equality here, which looks very much like this thing here. But we know that one of the coefficients is not 0. So we know this is 0 even though gamma 1 is not 0. Therefore, the kernel cannot be strictly positive definite. So we have a contradiction. Therefore, our initial assumption was wrong, and it's not possible that x1, or it's not possible that there is a point that's not in the other set, and it goes both ways round. So all points from the first set are in the other one, and vice versa. So therefore, we know that if the two means, so if this mean is equal to this mean, then all these points in this expansion appear over here and vice versa. So the two sets are the same if the kernel is strictly positive definite. Okay. So this can actually be generalized, but I won't show you the proof, but I'll show you the statement. But maybe just for this, for now, let's just remember that this mapping is quite interesting and that it doesn't forget any information. It somehow represents the whole data set as a single vector or as a single function in the reproducing kernel Hilbert space. So this mapping is an interesting mapping. So this means it's invertible mapping in that point, from that point of view. And the mapping has this property that if we take mu of x for some data set and take the dot product with some function f, so we write it down like this. We use the linearity of the dot product, so we can take this part out. And then over here, remember the kernel represents point evaluation of the function. So we get the function at a value, so this mu of x actually represents the operation of taking an average of a function on the sample. Could be a training sample or something like that. So that's kind of interesting. And the second thing is, if we compute this distance vector between mu of x and mu of y, one way to rewrite this thing is that's sort of an elementary property. I think it probably follows from the Cauchy-Schwarz inequality of functional analysis. We can rewrite the length of this vector as the largest value of the dot product that we can get by taking dot products between this vector and vectors of length 1, arbitrary vectors of length 1. So this here is actually the solution of this optimization problem. Now this in turn, if we use what we have just shown here, we have the dot product between this and this, minus dot product between this and this. So it's the difference between these two means of the functions. So that means the means of the sets x and y are different means, or is precisely the case if the function f takes different averages on this sample x and on the sample y. So a large distance in this space means we can find a function that distinguishes the two samples. Now we can, this solution of this optimization problem here, we can visualize that this function here is simply the function parallel to this, but normalized to have norm 1 in the Hilbert space. So it's this function. And we can show that function, and it's, maybe it gives some intuition to show it for a particular kind of samples. So if we generate the sample x from a Gaussian, standardized Gaussian, and we generate sample y from a Laplacian distribution, also with first mean 0 and first moment 1. So both distributions have mean 0 and variance 1. So they are not distinguishable based on the first two moments. But now if we map them into a reproducing kernel Hilbert space spanned by the Gaussian kernel, and the Gaussian kernel turns out to be a strictly positive definite kernel, so we don't lose any information. Even though the first two moments are the same, we should still be able to distinguish them. We can then look at which is the function that best distinguishes them. It's this function here. And so here's the dashed line is the Gaussian, the dotted line is the Laplacian, and the red thing is the function that best distinguishes samples drawn from the samples that we've drawn from these two distributions. And it's sort of an interesting function because it basically it focuses on the part in the middle where the Laplacian is higher, and on this part over here where the Gaussian is higher, and then in the end there's not much to see anymore. So this is a function that distinguishes these samples, and of course this function wouldn't be contained in the reproducing kernel Hilbert space of the linear kernel, and actually it also shouldn't be contained in the reproducing kernel Hilbert space of the polynomial kernel of degree 2, because the polynomial kernel of degree 2 essentially only looks at the first two moments. So now we can do the same thing for measures. So that's maybe the next 5 minutes are a little bit mathematical, but I think even if you get a little bit lost, you will be back on board later on. So this is just to show that we can generalize this from sets of points to measures. So it turns out we can also take probability measures, P and Q, and we need certain technical assumptions about certain expectations being finite. And then, rather than, so what did we do before? We took a set of points, mapped each point to the Hilbert space, and then took the mean of these points. So now we will take a whole probability measure, so in a sense infinitely many points. We map each point sampled from this probability measure to the feature space, and then we take the expectation. So it's just a generalization of what we had before. So this is a function in the reproducible kernel Hilbert space. This is the expectation of these functions. This will be finite under these conditions. And then we get an object which represents a probability measure in a reproducing kernel Hilbert space. And again, it will turn out that this object will represent an interesting operation on functions of the Hilbert space. Namely, in this case, it will represent the operation of taking the expectation of a function with respect to that measure here. And we can write down something similar to what we had before. So two probability measures, P and Q, will be distinguishable in the Hilbert space norm, if and only if we can find functions that have different expectations under these probability measures. Now, before we proved that for strictly positive definite kernels, this mapping mu was injective, so we could invert it from the mean in the Hilbert space. We could reconstruct the precise set that went into the mapping before. So now the question is, can we reconstruct the precise measure that went into this in this more general case? And the answer turns out to be yes, under some assumptions, and this is basically due to some classical results from probability theory. So there's this old result, which is actually interesting in its own right, which says that two probability measures, or two Borel probability measures, are identical if and only if we can find some continuous function such that they have different expectation. So that's kind of interesting. So if we allow for a large class of functions here, the class of all continuous functions is relatively large, to sort of transform our data, then actually differences in these probability measures will already show up as differences of their first moment, of their expectations. So if you, so in a sense, maybe this is something general, in statistics, either you can work with all moments or with distributions, or you work with a large class of nonlinear transformations, in which case afterwards it's enough to work with the first moment. And that's a little bit maybe philosophy of a lot of the kernel methods. We use a large class of nonlinear transformations, and then we can work with something simple. So that's another instantiation of this. And I'm not going to prove this, but the basic idea how to apply this to the case of kernels reproducing kernel Hilbert spaces is that for certain types of kernels, the reproducing kernel Hilbert space or some essentially is dense in the set of continuous functions, so every continuous function can be arbitrarily well approximated, and then we can actually replace this supremum over something different. Actually, it turns out that it's enough if we take the unit ball in the reproducing kernel Hilbert space and then apply this result for our setting, and we can prove that in this case, if K has a certain property which has been called universality, it's a property that was introduced by Steinwart for some approximation results using support vector machines. There's a later modification of Fukumitsu, slightly larger class of kernels. Fukumitsu has called characteristic, but I've written it here for the original one, for the universal kernels. So if K has this property, which for instance the Gaussian kernel does have, then this mapping that we showed before is injective, which means that two probability measures P and Q will be mapped to the same point in the reproducing kernel Hilbert space if and only if they are identical. So the mapping doesn't lose any information about these probability measures. So that's kind of nice. And it's also connected to a number of other things, and maybe there's some interesting topics here to work on that we haven't really explored. So it's related to something called the marginal polytope in a different context. And also what I find maybe even more interesting is that we can think of this kernel mean embedding as a generalization of what statisticians call the moment generating function of a random variable. And the moment generating function is defined like this. So I've already written it now in our notation. It's also an expectation of this particular thing. So there's this linear form raised or exponentiated. Statisticians have noticed that this kind of thing also sort of retains the information about the distribution of a random variable because you can generate all moments from it. For us, this makes perfect sense, because it turns out this thing here is a universal kernel. But we can also use other universal kernels and get these kind of mappings, and we don't lose information. Now, maybe I will skip this part. I just want to mention, in case someone is interested in this, so they can read up. Well, we haven't written much about it, but you can read what we have written or talk to me afterwards. This is related to some problems of optics. So maybe for the physicists, there's this process of optics, of diffraction in optics, in Fraunhofer diffraction. And you can ask the question, when is an imaging process invertible, depending on what size aperture you image through. People traditionally think that you lose information when you image through an aperture, which in a sense is true, but it turns out that as a special case of these results that come from machine learning, we can show that if we image through a finite aperture and we have a very weak form of prior knowledge about the probability distribution that forms the image that we are looking at. So for instance, if we know that this probability distribution has compact support, no matter how big, but it just has to be finite, then it turns out it's perfectly invertible. So this is, maybe as a side note, a connection. Okay, so maybe a more machine learning-like application is the problem of two sample problem. It's a low statistics problem. This problem means you're given two sets of observations, and someone asks you whether these two sets of observations have been generated from the same underlying probability distribution. So are they two classes or is it one class? And so for instance, you have some microarray measurements taken from different machines but of the same problem, and you want to know whether they are sufficiently similar that you can pool them into one to get a larger data set. And of course, this kind of criterion here, so now we know that this thing here is 0 for universal kernels. We know that this thing here is 0 if and only if the two distributions are the same. Now it's trivial to write empirical estimators of these things. We can basically we just map a finite sample to the reproducing kernel Hilbert space and compute this quantity for samples from P and samples from Q. Prove some results about that this converges or is consistent, and then we get some very simple criteria to compare two samples. This is an empirical estimator, which is just a double sum over these two samples that we want to compare with. And the interesting thing is that, of course, since this is working with kernels, so this H is defined from the kernel, we can also do this for all kinds of data where we can define kernels, so structured data, graphs, trees, strings, and so on. Yeah. And there's a second application, which is essentially also a two-sample application, and that's independence testing or dependence measures. And I will actually start on this one. So one way to do independence testing between two variables x and y is, at least formally, to say, well, the question of independence is just a question whether the joint distribution is identical to the product of the marginal distributions. And so if we could embed the joint distribution into our reproducing kernel Hilbert space and do the same for the product of the marginals, and then compute the difference vector, the length of the difference vector, we have a beautiful test statistics for independence. And of course, we need to do this now based on empirical data, and the simplest method, not the best, but it was the first one that we worked on, but the simplest method is to obtain empirical estimates of these two things. Is, first of all, if we have a sample of observations x and y, that's a sample from the joint distribution, so that's the thing that we embed over here. Now, given a sample of pairs x and y, how do we create a sample from this factorized distribution, product of the marginals? Well, one way to do that is simply to permute all the x's. So if we permute the x's, then the relationship between, so we have to write this. So I have a set of observations that looks like this. sampled from some distribution, joint distribution over x and y. Now if I take a fixed permutation, sigma, and I permute, sorry, x1, I do this permutation, then of course the pairs are no longer samples from the joint distribution. I have broken the dependence between the two things. But of course the x's are still samples from the marginal distribution of x, and sigma of y, sigma of y are still samples from the marginal distribution of y. So that these are nice samples from the marginal, from the product of the marginal distributions. So that's an idea how to do independence testing, and it works quite well. And you can, it's a real independence testing. It's not just first order. It's not just looking for zero covariance or something like that. Actually, what it is will depend on the kernel that you choose. So, for instance, if you take a polynomial kernel of a certain degree and you compute this kind of test statistics here. This thing, the empirical estimate of this, then of course you will test for independence up to a certain order. But if you take a Gaussian kernel, you will in principle test for full independence. Okay, so this one I think I'm going to skip. And then I want to talk about the representative theorem. But maybe now is a good time to briefly ask if you have any questions. There was one here and then here. Again, how many computations? How many permutations? Yeah. Well, in principle, you could take one permutation. Maybe you can do a better job by doing more. But in principle, already one gives you a sample. And yeah, you can do some, I mean, yeah, you could do all sorts of modifications, but in principle, you can do one. Yeah. Okay. There was a second question.
Yeah, I was just wondering, do people use kernels for compression then? That this, can you produce from one mean the whole data set?
So can you compress a data set by doing the kernel mean embedding? That's the question. Yeah, interesting question. So the rationale is we're not losing information by doing this mapping, and it looks like a whole data set is represented by this one object, of course, which in principle lives in an infinite dimensional Hilbert space. But so in a sense one could say we represent a data set by this function, and if we are able to encode this function more compactly than the data set, then we might have some means of compressing that data set. Now, so I guess there are two question marks. One is the question mark, can we compress the function more easily than the data set? Maybe that's the case. And if we can do that, how do we invert the mapping? So now we know in principle it's invertible, but we don't have an explicit form for the inversion. But actually that's inverting this kind of mapping is a general question in support vector machines and other kernel methods. It's related to what people call the Preimage problem. So in support vector machines, we typically, I keep talking about SVMs and haven't properly explained them yet. So we typically end up with, in the case of classification, we end up with a solution that looks like this, with a constant here. And it can be the case that, so this sum, well, I will say more about this later. It goes over all training points, but usually a large fraction of the alphas are zero. But nevertheless, you could still, if you have millions of training points, you could still have, I don't know, hundreds of thousands of expansion points where this does not vanish. So you might have a very, very rich vector in the Hilbert space. Now let's rewrite this a little bit. This is actually the same as saying we have a sum over, well, without sum. We have some weight vector and the dot product with phi of x plus p Now, if we were able to write this weight vector as a more compact sum, well, or in the extreme case, suppose we are able to write this weight vector as some w of z with a single point in the input space, then we could, then this thing here would be equal to the sign of, if you plug this in here, of just k of z comma x plus b. So then we would have only one expansion point, and it would be very cheap to evaluate this decision rule. So if you have a support vector machine trained on huge data sets and you want it to apply, you want to apply it to afterwards, and you want it to be fast in the application, then you would ideally want something like that, or at least you want an approximation of such a data set in terms of a smaller set of points. Now, if you want to compute such an approximation, then in principle you have the problem, you have a vector of this form that lives in the Hilbert space, and you want to approximate it, you want to find some z's and some betas such that this is a small sum, so this is a large sum, this is a small sum with few terms, such that this is close, and in principle, if you're given an abstract vector and you don't know how it's written in the high dimensional space, which is essentially the problem. If I give you the mean and I don't tell you how I've computed it, you just have this vector, this element of high dimensional space, and now you want to reconstruct what constituted this vector. So you would want to reconstruct these terms. It's in principle a similar problem to this kind of pre-image or reduced set problem. So it's a problem that has been studied in kernel methods. So I don't want to say there's the final solution to it, but yeah, maybe it's possible to do some compression, doing something like that. Yeah. Any other questions? Okay, so let's move on. So now the representative theorem. That's an important result in kernel methods. I've already alluded to it several times yesterday and today. So let me, it tells you that the solution of a large class of kernel problems are expansions in terms of finite sets of kernels. So that's a very nice theorem, and let's go through it, and we actually also prove it. It's not easy, it's not hard to prove. Okay, so we're given a positive definite kernel on some domain. We're given a training set. Actually, this is formulated for the real valued case, but it also applies for plus minus 1 for classification. So this one is for regression. So the training set, each input is from this domain, each output is a real number. We also assume a strictly monotonic function omega, which will appear down here. I'll say more about this later. And an arbitrary cost function. Maybe you don't have to parse this, just look at it here. So the cost function is something that takes all the inputs, the corresponding outputs, and always at each point what the function says about this input. So a normal cost function, for instance, would be just saying I compare yi to f of y1 to f of x1, maybe take the squared difference of the two, and I do this for all points and sum them up. That would be the typical mean squared error cost function. But this is a more general cost function, which in principle could depend on all of them jointly. It's not a big difference, but it turns out if we do it like this, we can also phrase things like Kernel PCA in the same framework. So the statement is, if we have such a risk functional, so this is the thing that we want to optimize, it contains this cost function part, and it contains a regularization part. So the regularizer is something that penalizes properties of the functions. In this case, it penalizes the norm in the reproducing kernel Hilbert space scaled by this monotonic function omega. So this function omega could, for instance, be just the square. So that's a monotonically increasing function, in which case we get a regularizer which is the square of the norm in the representing kernel Hilbert space. For instance, a support vector machine uses the square of that. but we can use a more general omega here. So the statement is, if this is the thing that we try to minimize, overall functions from our reproducing kernel Hilbert space H belonging to K. So I told you yesterday, every kernel K induces such a Hilbert space. We've shown how to construct it. So I solved this optimization problem, minimize this quantity over the whole Hilbert space, over this usually infinite dimensional object. That sounds like an impossible problem, and it turns out that the solution lives in a finite dimensional subspace spanned by the training points, essentially. So spanned by kernels centered on the training points. So the solution is an expansion, a kernel expansion in terms of training points. So that's nice. This turns this infinite dimensional optimization problem into a finite dimensional problem only consisting of finding these alphas. And the original form of this theorem is due to Grace Wawa, who's a famous statistician, or in between statistics and approximation in Wisconsin, and who has done a lot of work on reproducing kernel Hilbert spaces and spline smoothing. And we were always aware of this result, but it's written in a complicated way, and I never quite understood her proof. And at some point I thought this must be much easier, and I tried to prove it myself, and I came up with a proof that I'm going to show you now. And notice that the proof actually also works for these more general cases. Actually for, yeah, so it's, if you want, you can look it up in this paper. So it's a very simple proof, and probably it's essentially using similar arguments to the one of Grace Wawa. It's just easier, I guess. And the idea is the following. We take a general function in our Hilbert space. Actually, before I have called it H sub K, so it's the same space. It's just the Hilbert space that belongs to the kernel. So whenever we have a function in that space, we can decompose it into a part that lies in the span of our kernel centered on the training points, and into a part that's orthogonal. So this is possible in every Hilbert space. This is, for instance, a place where completeness of the space is used to define the orthogonal projection. Otherwise, the orthogonal projection might not exist. So you can define it as the limit point. As a limit point of some procedure. So anyway, so we can decompose every vector into a part in the span of our training points, kernels, and a part orthogonal. And orthogonal means, of course, that this orthogonal part is orthogonal to all these vectors defining that span. So this equality here is true. If we then apply such a function, so this is the general form of our functions. This is a finite expansion, the orthogonal part. We apply this general form of a function in our space to an arbitrary training point. We get the following. We take this dot product. Now we use the fact that, well, if we first just substitute this form in here. So we substitute this f, take the dot product. Now we use the fact that k, this k with this thing here, gives us again dot product between kernels. And it will be a kernel again, but more importantly, the second part, this orthogonal term, the dot product with the training point, will give us 0 by this assumption of orthogonality before. So that means this value of the function, which we get from this quantity, because the kernel represents point evaluation, will be independent of the orthogonal part f perpendicular. So the values of functions in our space at training points are independent of this component if the function is written like this. And that's already the main part. Now at the same, this was concerning the first part of the quantity that we look at. So the first part here is this thing does not depend on the perpendicular part. It only depends on the part that can be written like this. Now let's look at the second part. Second part, yeah. Well, let's just write down the second part. Again, we write f in its general form as the decomposition of something in the training points and something orthogonal. We just first rewrite this using Pythagoras. This is an orthogonality. And then we use the fact that sigma is strictly monotonic. Actually, also the square root in the positive domain is strictly monotonic. Therefore, this quantity is actually lower bounded by what we get if we just drop this part. Okay? So that means, and also equality occurs if and only if that part is actually 0. So that means the minimizer of this thing actually must have the orthogonal part 0, because the first part of our objective function was independent of the orthogonal part. So let's go back again. So we've shown that this thing here is independent of f perpendicular. This thing here, on the other hand, is minimized if f perpendicular is 0. Therefore, the minimizer of this risk functional, we're not saying that there's a unique minimizer, but any minimizer must have this property that the perpendicular part is 0. So therefore, remember we said that every function can be written like this. Now we've argued for the minimizer of the cost functional, this thing here must be 0. Therefore, the minimizers can be written like this, which is exactly what we wanted to prove in this theorem. Question, yeah? A norm is strictly positive, right? And the norm of a vector, if you have a vector whose norm is 0, then that vector is 0.
That's only if the norm is strictly positive, as in
every norm has this property, right? If the norm of a vector is 0, then the vector is 0. Is that what you mean? That's independent of anything else. It's independent of the kernel was strictly positive definite or just positive definite.
But the norm, if the kernel is not strictly positive definite,
yeah,
then the norm is just, it is not real a norm, it's just a semi-norm.
The norm in the representing kernel Hilbert space is always a norm. So if your kernel is not strictly positive definite, we proved it yesterday, we still get a dot product. So we proved that this dot product is strictly positive definite. So maybe that's slightly confusing, but we don't need the kernel to be strictly positive definite in order for the dot product of the reproducing kernel Hilbert space to be strictly positive definite. So that's that always works. Otherwise it wouldn't be a Hilbert space. Is it? Maybe I'm not addressing your question. So.
if we go to definition of strict positive definiteness, it's actually telling us that if you take the empirical maps, in whatever way you combine empirical maps of n different points using the alpha i's, that results in a vector with norm 0 if and only if the combination is a null combination, all the alpha i's are 0.
Yeah.
Predicting that would mean that there exists a non-trivial combination of empirical maps that results consequently in a non-zero vector in the RHS, which although has a 0 norm.
Well, so it could be the case. Maybe this addresses what you're saying. So if you don't have a strictly positive definite kernel, there might be. It's true. There might be such combinations that are 0, and you could always add such a combination to this kind of thing. And in particular, it could be that there might be combinations of kernels that are 0 that don't even lie in the span of the training points. But remember, I was careful when I formulated this. I did not claim. Wait. I did not claim that. So I'm just saying, if we have a minimizer, it can be written like this. It's possible that the same minimizer can be written in a more complicated expansion that doesn't lie in the span of the training points. Yeah? But we don't lose anything by restricting ourselves to points in the span to expansion in the span of the training points. Yeah? But thank you for the question. I think maybe this added some insights. Yeah. Okay. Any other questions? Okay, so this is a nice theorem, and there's several applications. I think I'm going to tell you more about SVMs in the next hour, so I will just tell you now that SVM is a special case of this. Also Bayesian, you can write Bayesian maximum a posteriori estimates as a special case of this, but only the maximum a posteriori case, although there are some algorithms where you end up with kernel expansion in terms of training points that are not map estimates. I remember there was some online method of Manfred Opper at some point that also had such an expansion, but he thought it was not following from the representative theorem. It just turned out like that some other ways, although maybe there's just a link that we haven't seen yet. We can also write kernel PCA as a special case with a more complicated cost function that combines all the training points. And yeah, so basically most of the kernel algorithms fall into this kind of framework. At least the kernel algorithms that produce a single function as a solution, that don't produce a distribution. So now we've seen the kernel is a similarity measure. It induces a linear representation of the data, and in the sense of the representative theorem, it encodes the hypothesis space of a class of functions that we are working with when we do a kernel method. So that's nice, because you could argue that these three questions are among the central questions of machine learning. And somehow the kernel is sort of an answer, or what, well, it addresses all three of them at the same time. And it also shows that they are intimately linked to each other, these questions. So maybe I can make kernel PCA quite short, because I think Neil has already explained it before I arrived. So he might have told you all sorts of wrong things that I cannot falsify now, but
because you weren't in my session.
Because I was late. I was still having breakfast. Shame on me.
You can watch the video, of course.
I can watch the video, and it gets really annoying at home. Yeah. So Neil told you that kernel PCA is best understood in terms of multidimensional scaling and optimizing complicated cost functions about how to place points in space. I'm going to tell you it's much easier. It's just looking for variance in data sets. So you all know PCA, and you all know, of course, what kernel PCA then does. You just map the data into the represented kernel input space and do PCA there. And it turns out this corresponds to all sorts of things. And I'm not going to go through the algebra. It's actually quite simple, the algebra. We just write everything in the feature space. We write the covariance matrix in the feature space. We write the eigenvalue problem. And we solve the eigenvalue problem. And it turns out this eigenvalue problem can be solved by diagonalizing this Gram matrix. We have to normalize the vectors in the reproducing kernel input space. We have to normalize the eigenvectors there, which gives us a certain type of normalization of these coefficient vectors. So every eigenvector can be written like this. And the normalization of this vector in the feature space corresponds to a somewhat funny type of normalization of these coefficient vectors, of the alpha vectors, where this lambda is involved. So you don't have to follow this in detail, because I think you get the idea. Once you have the normalized eigenvectors, you can take a point and project it onto these eigenvectors. So by this I mean you take a test point, you map it into the feature space, project it onto the eigenvectors. That gives you a function or a real value. So these are the feature extractors, if you want. So one way to think of PCA is the feature extraction method. And the feature extractors look like this, which actually also follows from the representative theorem. And that's it. And maybe just to draw a parallel to yesterday. Yesterday I showed you at some point someone asked about this issue. You map points into the feature space. You take a point, map it to the whole function. And I said, well, that means we represent each point by its similarity to all other points. But we can also use similarity to a discrete set of points. And then we ended up with a map that looked like that, where this thing here was there in order to make sure that if we map 2 points into that space and then take the dot product between the two, we recover the kernel. Now it turns out that this is also related to kernel PCA. Namely, if we use the diagonalization of k, so we write this quantity in terms of the spectral decomposition, this is also related to the functional calculus that I told you about yesterday, then k to the minus 1/2 can be written like this. So if we plug this representation of k to the minus 1/2 in here, we get this quantity here. So this is one of these discrete or empirical feature maps based on finite sets. Now notice we can drop this first u because it's a unitary matrix, and unitary matrices leave the dot product invariant. They're just rotations. So we can actually ignore that, because in the end we're only interested in dot product in our reproducing kernel Hilbert space or in our feature space. So let's drop that. If we drop it, we get this thing here. And it turns out that's exactly the kernel PCA representation. So that's the representation we get by projecting onto all kernel PCA eigenvectors. Because the rows of this thing are the eigenvectors, so these are the alphas. So this gives a sum over the alphas and the kernels, and here this gives us this normalization by the square root of the eigenvalue. So that's also related. And here's a toy example of kernel PCA with a Gaussian kernel. So this is, I remember it was actually a very painful process to publish that paper, even though it's now one of our most cited papers, but the reviewers really didn't like it. So if you have, at the time this was something quite different, and if your papers are too different, people don't like it. So maybe now is a good time to discuss about reviewing quality. We were talking about reviewing quality the other day because the ICML reviews had come out. And it's a bit of a sad story in machine learning. It's actually worse in some other communities, I think maybe computer vision, that reviewers seem to think the job of the reviewer is to find weaknesses in the paper. But I think the job of the reviewer is both to find weaknesses and to point out what are the strengths of the paper. So what is interesting about a paper. And I think Neil was telling me that when he ran AI stats, he explicitly asked reviewers to point that out. But people just ignore that. They are very much in this mode of only looking for what can be criticized about a piece of work. And then we end up with a lot of papers that are hard to criticize, maybe partly because they're just very technical and get accepted. And sometimes we miss out on original papers that maybe can be criticized but have a really interesting new idea. So now I don't want to claim this just applies to my papers, but I think Neil has some comments. We did publish it in ICANN, but we got basically no reviews, and it was a poster. But now I'm talking about the journal version. We sent it to neural computation, and it took 2 years. And but then in the beginning we only had the polynomial kernel, and then at some point we also did the example with the Gaussian kernel, and I think the reviewers liked that one more.
You you presented it as a poster at the summer school in '97.
That's right.
So it was first presented as a summer school poster.
Yeah, this work was first presented at a summer school, in the same summer school where we got to know each other. And yeah, and I remember then when we did the final proofs, the lady from MIT Press was asking which way around this image goes and whether these things are cells. But I think they put it on the title page. Anyway, so the image is simply a toy data set with 3 clusters of data. We use a Gaussian kernel and compute the projection of the data set. Well, no, we could compute the projection of test points onto the first, second, third, and so on principal component. This gives us functions in the input space. They are nonlinear functions, so we cannot show the principal axes. We can only show the effect of taking a point, mapping it to the feature space, projecting it onto an axis. The first axis then in the input space corresponds to the separation between these 2 clusters. And it just ignores that cluster. It's kind of funny. The second projection, now remember the second component sort of looks at the space orthogonal to the first one. The variance corresponding to the first component has been projected out. So now, in that sense, the distinction between these 2 clusters has been projected out, and the second component therefore doesn't distinguish these 2, but it only distinguishes this from the union of these 2. And then the next component, now these 2 components together separate the clusters, you could say, and the higher order components look at structure within the clusters. So this component looks at structure in this bottom right cluster, this component looks at the bottom left cluster. This looks at the top cluster. This looks at the top cluster again, but orthogonal to this direction. And this one is roughly orthogonal to this one, and so on, and you get a higher order structure as you move to the higher order components. And also I wanted to point out that this method is, of course, I think you've learned that already in Niels' course. It's related to all sorts of things. It's related to it's related to multidimensional scaling, with the difference being that, well, first of all, it comes from a very different direction. It comes as a generalization of PCA, as opposed to an embedding problem. But maybe more importantly, the difference is in kernel PCA, of course, you get a global embedding of data, so not just of the training data, but also of test data. So all the feature extractors are functions defined on the whole space, whereas in multidimensional scaling, you're given a discrete data set and you're asked to embed that data set and nothing else. So that's also can be done by kernel PCA. In that case, I like to tell Neil that multidimensional scaling is a special case of PCA, which he doesn't like because multidimensional scaling is older. Anyway, logically, it's a special case of kernel PCA, and logically, and it can be done with all positive definite kernels. Maybe the same is true for multidimensional scaling. Although whenever I see as multidimensional scaling, it's done for stationary kernels that depend only on the distance. Okay, he's shaking his head. Okay, so logically it subsumes multidimensional scaling, and it subsumes also some other methods, and we have a paper about that where we show that it contains locally linear embedding and the Laplacian eigenmap, and in some limit, because isomap doesn't always correspond to positive definite matrix, in some limit also isomap. So if you're interested in data in dimensionality reduction, that's an interesting connection to look at. So much about PCA, and we applied it to some problems, but I think most of the applications were done by others. I think it has been applied in a number of domains, such as computer vision, so I'm not going to go into that. Well, maybe just briefly, but I think you don't see much anyway. So this was an application to super resolution where we trained PCA on some high resolution images, and then we took low resolution images and project them onto our learned PCA basis, and this way could reconstruct higher resolutions. But I think on this, so basically what you should be seeing is that this reconstruction is sort of similar to the original, and it's better to these other methods, better than these other methods, but maybe you don't see it on this projector. Okay, so now support vector machines. Any questions about this part? All right, so I think we have enough time left for support vector machines. So you've heard about them several times. The basic idea: map the data into the feature space. Computer separating hyperplane will correspond to a nonlinear separation in the input domain. So I'll show you in detail how this separating hyperplane is computed, and hopefully I can also show you proof of bound on the VC dimension or something like it of optimal margin or large margin separating hyperplanes. Okay, so the hyperplane, a hyperplane can be written by such an equation. A hyperplane is a set of points satisfying this kind of equation where W is a vector that's not equal to 0. W is the normal vector of the hyperplane, and B is an offset. And this hyperplane can be thought of as a separating one, because this quantity here takes positive values on one side, so in one half space, and it takes negative values on the other side of the hyperplane. However, we can also define an optimal separating hyperplane based on two data sets, and by this we mean the hyperplane which has the largest distance to any of the points. So it separates the points correctly, it's one class, the other class, while satisfying the constraint that the closest point to the hyperplane has maximal distance. So the distance of the closest point is maximized. And one way to get this is to take the convex hulls of these sets of points and then just look for the shortest connection between these two combined hulls, and that will give us a normal vector. Okay. Now note that there is a scaling degree of freedom in this whole business. Namely, if we have a hyperplane defined by this equation, we can multiply this equation by some number that's not 0, which gives us a different weight vector and a different offset, but the set of points that solve this equation is still the same. So there's a degree of freedom. It's like a gauge degree in physics. This thing here describes the same hyperplane as this thing. And one way to remove this was a definition by Wapnick, who said that I would call a hyperplane to be in canonical form with respect to a given data set if the scaling is such that for the closest points of the data set to the hyperplane, this thing here has modulus 1. Okay, so it's, if you look at the picture, it's easy. Remember, on this side, the hyperplane takes positive values, here take negative values. We just scale it such that for the closest point, the value is plus or minus 1. Okay, so now for the canonical optimal hyperplane, the picture is as follows. We have a set of points here, plus 1, label plus 1, here minus 1. Here's the hyperplane, this equation. The value of this quantity here is plus 1 over here. For this closest point, it will be minus 1 over here, because this hyperplane intersects it in the middle, so there will be at least one point where it's plus 1, at least one where there's minus 1. And it turns out for these canonical optimal hyperplanes, one can relate the distance between these two classes to the length of the weight vector as follows. Take the point x1 and x2. So for x1 we have this equality. For x2 we have this equality. We can take the difference of these two equations to get a 2 on the right hand side, and here the difference vector. Now let's divide this by the length of w. So we get this equation. So what does it mean? It means here we have the vector x connecting x1 and x2, that's this direction. And here we take the dot product with a unit vector in this direction. So that means we just take this vector connecting to these two things and project it onto the direction orthogonal to the hyperplane, which means we are measuring exactly the distance between this dashed hyperplane and this second dashed hyperplane. And this thing is sometimes called the margin. It's the margin of separation of two classes. So this is the margin of separation, and the margin of separation is 2 by the length of w. So therefore, if we want to compute the optimal hyperplane, what we should be doing, we've had this already, what we should be doing is we should minimize the length of this w in order to maximize the distance between these two classes, subject to the constraint that for all positive points, this quantity here is at least plus 1, and for all negative points, this quantity here is at most minus 1. That will give us the optimal hyperplane. But before I write down the optimization problem, I want to show you the theoretical result. Do I? Yes. Which was formulated by Wapnick in this form. There was a little bit of confusion about this at the beginning, in that it's actually best formulated with a slightly different quantity. I'm doing it in terms of the VC dimension. I don't want to confuse you, but the thing is that actually this definition of the canonical optimal hyperplanes depends on the set of points, and if you on the training points actually. And normally, if you choose a class of functions and you compute its VC dimension, it shouldn't be depending on the training points. So there's something slightly different capacity concept. You can essentially prove bound with that capacity concept, and then everything is fine. But I don't confuse you, and I'll simply say I have a set of points here. I'm not going to say they're the training points. There's just some points, and then I can give you a VC dimension bound. So what is the theorem? Theorem is we have hyperplanes. For simplicity, we don't have an offset here, but that doesn't make a big difference. It doesn't increase the capacity a lot. We assume W is normalized in canonical form with respect to this set of points here. So this equality here is true. Then this set of decision functions And these now, in this theorem, these set of decision functions are only defined on these points, which is a bit of a stupid thing because in reality we want to define them on other points as well. But this set of decision functions, if we additionally place this constraint on the length of W, so we want short W's, which means since W is inversely related to the margin, we want large margins. So if we place a lower bound on the margins or an upper bound on the length of the weight vectors, we get a VC dimension which is bounded from above by the square of this constraint and the square of the radius of the smallest sphere containing the data set. So this is, second thing basically fixes the scaling of the data set. Otherwise, you could just obtain a larger margin of separation by blowing up your data. Of course, that doesn't make sense. So we fix the scaling of the data set. We could just say it's 1, or we put it in here. But the basic story here is the shorter the length of the weight vector, the smaller the VC dimension. And we can prove that using an idea proof strategy of Gurwitz. Yeah, so let's go through this. It's maybe 3 pages, the proof, and I think it's going to be the last proof of my course. So we assume that our set of points are shattered by canonical hyperplanes. So shattering, remember from 2 days ago, shattered by canonical hyperplanes satisfying this constraint. Shattering means that no matter how we label our data set, so for any set of labels in plus minus 1, we can do this kind of inequality. So remember, where does this inequality come from? I told you before that an optimal separating or a separating hyperplane in canonical form has this property that the positive points, for the positive points, this quantity here is at least plus 1 or larger. For the negative points, this quantity is minus 1 or smaller. Now, if we multiply this thing here with the label, we can write both inequalities as 1. And the inequalities will exactly look like this. So shattering means now that no matter how we put the labels, we can always satisfy this inequality by the choice of some W that satisfies the constraint that is length. So shattering by canonical hyperplanes with this constraint means no matter what the labels are, we can always satisfy all these inequalities with such a hyperplane. So let's assume that this is the case and then see what follows from it. So it turns out that something follows about the VC dimension. And the proof will first show that the more points we can shatter like this, the larger a certain quantity must be. Is this quantity here? And in the next step, we will show that this quantity is actually upper bounded in terms of a radius of the smallest sphere. And if we put these things together, we will get a bound at the VC dimension. So we first get a bound on how many points we can at most shatter, which gives us the VC dimension. Okay, so let's take this thing here and sum it over all R. So we sum it over all points, which gives us an R on the right hand side, where we had the 1 before, and here we just have the sum over all these things. So just going back and forth, we have moved the yi inside, and how here we have the sum over yi xi. So that's an inequality here, and on the other hand, we can upper bound this quantity using the Cauchy-Schwarz inequality. So this dot product is upper bounded by the length of the first argument times the length of the second argument. Now the length of the first argument by assumption is upper bounded by lambda. Now we know that this thing here is upper bounded by this. At the same time, we know that the same thing is lower bounded by R. Therefore, R is lower bounded by this, or R divided by lambda is lower bounded by this. Okay? You tell me if I'm going too fast or too slow, or you just ask whenever you get stuck. So that's our first result, very elementary. So the second one is also simple, maybe a little bit less elementary. Now, by assumption, no matter what the labels are, we can do that. So we are free what to do with the labels. This inequality is always true. Let's consider a particular type of labels. Labels that that are independent random variables, taking values plus minus 1. These are also called Rademacher variables, this kind of random variables. And let's see, look at this quantity, which is the quantity that we had on the previous slide. Let's see what the expectation of this thing here behaves like, of the square of it. Okay, so we first rewrite this thing here as a dot product of the thing with itself. And we can take the expectation out. Well, or we keep it out, sorry, we take the sum out. We can do that because expectation is a linear operation. So we take one of the two sums out, and then we take a look at how does this thing here behave inside. Well, how does it behave? There are actually two paths. One of them in this sum, one of them is the part where the labels are, the indices are different from here. And one of them is the part where the indices are the same. And let's deal with them separately. So the first one, where the indices are different, we can put together with the expectation in this term. The second one, where the indices are the same, we put together like this. Now it turns out that the first term vanishes for symmetry reasons, because these yi's are independent Rademacher variables, so they will sort of all cancel each other. Whereas the second term is something that's left, and the second term looks like this. And so this is our second term here. This is just the norm of this vector. And of course the yi's don't change the length of, don't change this norm, so in the end we're just left with this xi squared, and we don't need an expectation anymore because everything that's random is gone. Okay, so since now we use our second assumption, which is all the points are contained in a ball of radius r, so we know that this is true. Therefore, looking back, so we know that this quantity here is upper bounded by this. We know each one of those is in the ball of radius r. Therefore, this quantity is also upper bounded by r squared. And well, and we have lowercase r times this r squared. So we end up with this thing here on the right hand side, which we have derived using which holds true for the expectation over the random choice of the labels. Okay, this is a statement only in expectation. Now we want something that's we want this expectation to go, because we wanted to combine this with this other statement that we had about this quantity. Now, if something is true for an expectation, then there must be at least one set of labels here for which is also true. I mean, if for all the labels this, if an inequality is true for an expectation, then there must be at least one instantiation where it's also true, because if it were violated for all instantiations and we take the expectation over it, then in expectation it would also be violated. So let's pick that one, there are probably many, but let's pick that one set of label, that one of those sets of labels for which this inequality holds true. So far we haven't fixed the labels, now we fix them. For that one set, this inequality is true. And this is what we're going to combine. So now in the first part of the proof we have shown that this is true. In the second part we have shown that for a specific set of labels this is true. So this first thing was true for all sets of labels. This was true for a specific set of labels. We're going to use that set of labels everywhere also here. And now we combine these two things. So this is the same as here, so we can sandwich in between. So this is lower bounded by this, which is what we've written here. We take the lambda squared to the right hand side and divide by lowercase r, and we're left this thing with this thing here. So what have we shown? We have shown that if we assume that W is upper bounded by lambda, the data set is shattered, data set of r points is shattered by canonical hyperplanes, the data set is upper bounded in length by R, then as a consequence of these assumptions, the number R must be upper bounded by this thing here. So if a data set is shattered, it cannot be larger than this. Therefore, this is an upper bound on the VC dimension, because the VC dimension is the largest number of points that can be shattered.
Can you repeat what is big R?
Big R is, let's see, where is it written? It's the length, the radius of the smallest sphere around the origin that contains the data set. And we use it in the proof, I think in the second part. So in the second part we derived this upper bound on this quantity, and now we were saying each one of those is upper bounded by R squared. So then we got this thing here. Yeah. Okay, so basically we have two things. One is the radius of the smallest sphere containing the data points, and one is in a sense the radius of the sphere containing the weight vectors that are allowed. So it's an upper bound on the length of the weight vectors. Okay. One can also intuitively understand why it's reasonable to have this kind of bound on the VC dimension, that this margin should play an important role. One way to think of it is would be to say, well, and this is just a purely intuitive argument, what if we have some kind of noise on the data points? So there's, for instance, there's an old paper about neural network by Chris Bishop that argues that putting noise on the data amounts to Tikhonov regularization on a neural network. So putting on noise on data is some form of regularization of a function class also implicitly, and here we could say if we were to put bounded noise on each data point, maybe we sample from each data point many points with a distribution that has this bounded noise, and then we train a normal hyperplane without looking for optimal margin, we might get something which is similar to this maximum margin kind of hyperplane if the radius of the noise here is as large as it can be. Or another way to interpret maximum margin would be in terms of minimum description length. So minimum description length is an approach to inference or generalization where you try to say finding a function that generalizes amounts to finding a short description of the data set, amounts to a compression of the data set, and the smaller the compression, the better we can generalize. And here you can also think of a large margin hyperplane as a compression of the labels of a data set. So we are given the data points, and what we're going to do is we throw away the labels and instead store the hyperplane, because we know we can regenerate the labels using the hyperplane. And it turns out that if your data lies in a ball of bounded radius, and if the margin of separation is large, is rho, then you can work out how accurately you have to store this angle. So in this simple picture here, storing the hyperplane amounts to storing this angle gamma. And the larger the ratio of rho to r, the smaller or the looser you can store gamma, the less accuracy you need for storing gamma, and therefore less bits. So, and if you work this out in this simple picture, you end up with this ratio of rho over r. So anyway, so now let's forget about the theory. Let's just accept it's good to classify data using large margin hyperplanes, and then let's just think about how we do it in practice. So remember this picture from before here. So we said what we want to do is we want to find the separation of these two classes of data points which has minimal w, therefore maximum margin, minimal length of w, while satisfying the constraint that this thing here is at most at least +1 on the positive side, at most -1 on the negative side. So let's write this as an optimization problem. We minimize this quantity here, subject to, and this again, this is our compact way of writing these two constraints. Positive class larger than +1, negative class smaller than -1. And this is a constraint optimization problem with inequality constraints. And the way to solve it is using Lagrange multipliers. And I think when support vector machines started, this kind of approach was quite rare in machine learning, but now we have lots of optimization problems and people are getting quite sophisticated about optimization. And we're actually having a full course here on optimization on, I think, tomorrow and on Monday by Rob Vanderby from Princeton, who's actually indirectly connected to machine learning, because when we worked on the first algorithm for support vector regression, we needed an optimizer that had certain properties, and Vanderby had developed an algorithm he had called Lokbo, and we ended up, and he had code on his homepage. We ended up using his algorithm for support vector regression, and then later I learned he's also an avid astronomer. So I was thinking maybe we can lure him to La Palma to do some astronomy at night. By the way, I should also say if there's some amateur astronomers among the audience here, talk to me afterwards, because we want to do some astronomy work as well. Anyway, so this is, so he will tell you much more about optimization and probably more sophisticated stuff. I just want to give you a basic intuition about how constraint optimization works. So first I'll tell you what we do, and afterwards I'll tell you why this seems to be something sensible. So what we'll do is we introduce Lagrange multipliers and a Lagrangian, and the Lagrangian is the following. You take the objective function and then you subtract the multipliers times the constraints. And the constraints in the form, so we actually move the 1 to the other side, we subtract 1, so we have this thing -1 is non-negative. So remember, this thing -1 is actually written here. This thing -1 should be non-negative, and this kind of constraint is just subtracted from the objective function with these Lagrange multipliers. So it looks like magic. Why do we do this? And then the prescription is we have to minimize this so-called Lagrange function with respect to the original variables, W and B. They're called the primal variables. And maximized with respect to the Lagrange multipliers, which are sometimes called dual variables, which will become clear in a minute why. So why is that a good idea to minimize with respect to W and B and maximize with respect to alpha? Let's see. So if what happens if a constraint is violated? So a constraint being violated means that this thing here will be negative, right? So if this thing here is negative, then, well, we said we are maximizing L with respect to the dual variables. Therefore, since this thing here is negative, and also we have a minus here, so the overall effect is positive, the multipliers are positive, then, of course, by growing the corresponding alpha I, we can get a larger value of L. That's what the alpha I wants to do. So the alpha I will start to grow. Now, at the same time, W and B's goal is to minimize L. So W and B want to decrease the value of L, so they have to change, and the only way to stop alpha I from growing L beyond bounds is to make sure that this is no longer possible. So W and B have to change such that this constraint is no longer violated. So that means geometrically the hyperplane has to shift around such that the constraint is satisfied. In other words, geometrically the hyperplane has to shift such that for the point that previously was violating the constraint, this is no longer the case. So the position of W and B has to change until this stops. And if the problem is indeed separable, so if there is a solution, then this will have to stop before alpha I has become infinite, so there will be some finite value of alpha I where it stops. Now vice versa, what about if a constraint is trivially satisfied, but by that I mean not as an inequality, not as a normal inequality, but as a strict inequality. So that means in our picture from before, what if we have a point like this? So this point also has a constraint, that yi times this thing here must be -1 must be a non-negative. So this point here trivially satisfies that constraint. It doesn't touch the constraint. Okay, so that's a trivial one. In that case, I claim that the corresponding alpha must be 0. Why is that true? Well, if this were true, and at the same time the alpha I that corresponds to it, so this is yi, alpha I, were non-zero, then we could actually increase L by decreasing the alpha I. Right? Because remember, alpha I wants to increase L, and therefore it doesn't want this negative term to be too large. It's a negative term in this case. If this is positive, here we have a minus. So the corresponding alpha I should better get 0, otherwise we pay something that we don't want to pay for. And this is called the Karush-Kuhn-Tucker conditions. They're saying that either the constraint is 0 or the Lagrange multiplier is 0. Possibly both of them could also be 0 at the same time, but that's unlikely. Okay, so we will get back to this in a second. This will be important for the support vector expansion, but before we do, let's derive what's called the dual problem. It goes as following. Remember, the Lagrange function wants to is a saddle point actually. It's when we maximize with respect to one set of variables, minimize with respect to another one. But of course, at this saddle point, we have these conditions that the derivatives are 0. If we take the derivative of L with respect to B, we get this equation here. If we take the derivative of L with respect to W, we get this equation. So I think you see if we derive by W, we get a W here, and over here we pick up something with alpha, y, and x. The rest is nothing. So we get W equals this thing here. Likewise, if we take a derivative with respect to B, this thing here vanishes. The only thing that we're left with is whatever is in front of multiplies B, which is the yi and the alpha I and this sum, which means that we get this condition. We substitute both these conditions into the Lagrange function because we know for the optimum they must be satisfied. If we do this, we get this Lagrange function, or we get this function, which is now no longer dependent of the primal variables. Only the dual variables appear. And remember, the dual variables we want to maximize with respect to the dual variables. So this is now a simple maximization problem. It's no longer a saddle point. And we're left with this this constraint here that was from the start. This constraint that came from the derivative with respect to B. And it's important when we look at this to notice that this quantity here only depends on dot products. So this is something where we can substitute kernels. And moreover, if we take another look at these conditions that we had from the saddle point, this was the first one that we're just keeping until the end. This condition is called the support vector expansion. It tells us that the solution of W is actually a linear combination of the training points. This corresponds also to the representer theorem. And remember that we had this observation from the last slide saying that whenever a constraint is satisfied as a strict inequality, the alpha I is necessarily 0, which means that the corresponding point xi does not appear in this expansion. On the other hand, if this equation here is, we know that the condition is that it's greater or equal to 0. So in the end, there's just these two choices. It's so greater or equal to 1. It's either greater or it's equal. And if it's equal, that means geometrically the point lies on the margin. In that case, the alpha I can be non-zero. Typically will be non-zero. The point does appear in the expansion, and it's called a support vector. And if we substitute this thing here into our form of the decision function, which looks like this, so that's just, remember the hyperplane was characterized by the set of points where this function is 0. And so the decision function is just looking whether this quantity is positive or negative. We substitute W in here. We use linearity of the dot product. We end up with this thing here, which only depends on dot products, and also which only depends on the support vectors, because for the non-support vectors, the alpha I would be 0. Okay, so now we can kernelize this thing, and we can kernelize the dual problem, this thing here. And we get a problem. This is also a very old slide from the days when people were still thinking of neural network, and we had to tell them that this actually is a kind of a neural network.
It's now appropriate again.
Yeah, and I kept it all these years. I
It's now back in fashion.
always believed in neural networks.
Like Claire flares.
And and then we get a kernelized support vector machine, which gives us a decision rule like this. Now, maybe just very briefly, we can modify this to non-separable problems. So before I was always assuming there is a separating hyperplane. Maybe there isn't in practice, but there's a simple modification which turns out to lead to a simple modification also of the dual problem. Simply, we introduce what's called slack variables. It's a trick from the optimization community. Non-negative slack variables that soften the constraints. We will penalize the slack variables in the objective function by introducing some term here. And it turns out we get a dual problem which looks like this. The dual problem is exactly, first of all, is the same as before. The only change is that we have here an upper bound on these coefficients. So before, remember when I told you about the contradiction, if a constraint is not satisfied, the corresponding alpha I will start growing. Basically, this just says, well, we just stop it at some point. That means the constraint won't be satisfied strictly without slack variable, and the point might be misclassified. That's the standard way of doing the soft margin SVM. There's another way, which is a different parameterization. It's not in terms of this C, so this is a new hyperparameter that then we somehow have to fix or optimize. There's another one, it's called the Nu-SVM, which has a different hyperparameter, which has a more interesting interpretation. This is just like an arbitrary trade-off constant. Here we have a parameter, a slightly different objective function, for which in the end one can prove that it characterizes essentially this parameter nu. We can prove that it's an upper bound, or it's a lower bound on how many points will become support vectors. It's an upper bound on how many points will violate a constraint. So an upper bound on the points that are either misclassified or lying within the margin. And we can also prove that asymptotically both these inequalities become equalities. So therefore, if we use this formulation in terms of the new parameter instead of the C, it gives us, we sort of control the trade-off between the smoothness of the solution, or the margin of the solution, and the how many training errors we want. We control that trade-off simply by specifying how many support vectors we want, which is sometimes nicer. And the dual problem is similar. It's actually a little bit, this functional is a little bit easier in that case, but there's one additional constraint. But the decision function always looks like that. Okay. Now, nowadays, if you want to train an SVM, you download some piece of code. I guess very few people still implement their own SVMs, and there are specialists doing SVM implementations and competing for who can solve huge data sets of millions of points more efficiently. So this has become a very relatively specialized domain. But maybe just here the basic idea. So naively, if you want to maximize this, you would find that it scales with the power of the training set size, which is not great. But the first idea is that only the support vectors are relevant. So if you knew beforehand which of the alpha i's should be 0 in the end, you could restrict yourself to just solving this for the support vectors. Now you don't know this beforehand, but you can sort of iteratively do things. You can go through the data set, see which points become support vectors, throw away the rest, train on the support vectors. You revisit the other ones later on, see if one of them is a support vector after all, and so on. So you can do things like that. which means like optimizing the problem by iteratively looking at sub-problems, and there are various versions of doing something like this. Even there's a version where the sub-problems only consist of 2 points, or maybe 3 points in the case of a Nu-SVM, in which case the sub-problems become analytical, and the problem of optimizing this sort of then becomes the problem of how to choose the sub-problems, when to optimize over which pair of points, and so on. So this is a specialized field, and here again the handwritten digits that we've all come to like over the years. So this is not the USPS set. This is already the more advanced version, the MLSS set, which was a bit bigger. So I remember when I joined AT&T Bell Labs to work with Abnig on this, they already had some results on the USPS set, but not on MNIST. And Jan de Kuhn was always teasing us and says he's not going to take support vector machines seriously before we have a good result on MNIST. Well, actually, I think they had something, but it was not a good result. And then we managed to get a good result, got what at the time was a record result using some variant of SVMs that was translation invariant. By now, the world record is significantly better. There are SVMs that are much better, and I've lost track who holds the current world record. It's probably either an SVM with some invariances or a huge neural network with invariances. And in a sense, it doesn't matter, because we are basically at the point where we can solve this problem as well as humans can do. So it's a good sanity check if you can solve it, but it's maybe not the most challenging problem of machine learning that's left. Okay, so with that, I would like to stop and maybe take a few questions before you go for lunch. Thank you very much.
What's the probabilistic interpretation of the SVM?
Probabilistic interpretation of SVM is an interesting question. There's a number of papers on this. There was a paper of Pete Solich, so the difficult bit is sort of what happens in the margin. He had some kind of solution where basically you have to introduce a third class where you don't know. People were not completely happy with it, but it's some kind of interpretation. We also had a recent paper at ICML. Neil he also has some kind of, what is it, the importance vector machine? Or
No, it wasn't. It was, Pete did this thing where you have a third category, you have 3 categories. I don't know if he did it or we did it first. Anyway, his solution wasn't normalizable. The probabilistic solution is that you've got 3 categories. One is in the middle of the other 2. You've got a +1 like a 0 category and a -1. And the 0 category you never observe. And you have a prior that you're never going to observe it. And so it's like, you just never observe it. Now the problem is if you allow the model to learn the parameters, it decides that category doesn't exist. So you have to force that category to exist. And it's useful. We used it for semi-supervised learning in Gaussian processes. And it is properly probabilistic, but it's a little bit weird. But Pete's one didn't normalize. I think he had an approximate thing, but that one properly normalizes.
Okay, so if you're interested in that, you should look at Pete's paper, you should look at Neil's paper, and there's a paper of a recent ICML. The first author is, actually I don't remember, I can send you the paper if you're interested in that. Alex Teen is also one of the authors, Z-I-E-N. Maybe a general question is, of course, about the relationship between discriminative and generative learning. So some people would argue that the SVM is a discriminative method which tries to directly find a discrimination, and maybe not every method that finds a discrimination has to be built on a generative model. So typically when you say you want a probabilistic model, typically what people would mean is they want a generative model, and that might not always be possible. So sometimes it might be easier to directly model some property of a conditional distribution, which is what the SVM is doing, but maybe that's a question of philosophy at some point. So people have slightly different opinions on that. You want to add something?
I don't think it matters.
It doesn't. Okay.
I think sometimes you want to do the discriminative and sometimes you want to do the generative.
So it's it's an interesting question. So I guess maybe 5 years ago people were thinking discriminative learning will always work or will typically work better on competitive problems. Now people are moving, maybe in computer vision, there's a lot of interest again in generative problems. And people think if you have a full generative model of things, that's going to be the gold standard in the end.
Part of it's branding, part of it's saying...
Part of it is branding, that I agree.
Yeah, so, and actually the truth is probably somewhere in between, but that's a difficult branding.
The truth might be in between, and it's not clear that we should be solving all problems in a generative way. Like you can probably recognize many images that you cannot visualize vividly, or you cannot draw images that you recognize. So it's not clear that we as animals use generative models for everything that we do. So we might be able, or maybe I can understand Spanish reasonably well because my kids speak Spanish, but I cannot speak it well. So I don't have a good generative model of Spanish, but a reasonable discriminative model. So we were discussing this kind of topic the other day. So it's yeah, maybe it's a question of taste. There's a question here and here.
How can you solve multi-class problems with SVM?
So how do you solve multi-class problems with SVMs? The first approaches were simply to decompose, or most approaches decompose multi-class problems into one-class problems, either by saying we trained, for instance, if we have 10 classes, we train 10 classifiers, each of them solves one versus the rest, and then we do some kind of voting in case several of them want to say yes. There's also other multi-class approaches that solve for all pairs of classes. It's a larger class of two-class problems, but they are a bit smaller. Then there are multi-class or reductions to the two-class problem by having some kind of graphs where you, or trees where you take decisions. So you always separate between groups of classes. And there are some formulations of SVMs that directly solve the multi-class problem, but then they tend to be more expensive to train. So there's different such methods. Yeah. So there was another question somewhere over here. Yeah.
And my question is related to the first question. When you have the case, for example, of multi-view learning, or usually using generative models, is you have some probability that you can easily combine. So how you can you combine easily different SVMs output?
So one method that people have used a lot so there's a trick by John Platt who basically says, well, we look at the real valued output of an SVM, and then afterwards we fit some logistic function to it to estimate the conditional probability, and it works surprisingly well. So you can do something like that, even though there are some theoretical reasons why it's a little bit broken, but in practice it seems to work quite well. But this is also a question that's addressed effectively by these papers that give probabilistic versions of SVM. So if you're interested in that, you should look at these 3 papers that were mentioned before. I think they would give you also approaches to do this kind of thing.
But it's also true that very often, even if a Gaussian process gives you a probabilistic output, and there were workshops on this, it's often not very well calibrated. So if you try and see what its probability says against what you get when you start looking at examples, you see it's poorly calibrated anyway.
Right.
So I think, and that's actually I don't think that question is solved.
It's actually very nice that you would say that, because usually this is pointed out as a strength of Bayesian approaches, that you get these probabilities, but of course these probabilities are always subject to what you put in at the beginning. So for instance, to your prior, and you can make these probabilities very, very wrong by putting in the right thing to begin with. And there has been, if you're interested in this problem, there has been, I think there's a paper that you might also be a co-author of after this competition that Joaquin was organizing about. Okay, so there's a paper comparing different approaches in that regard. There was a competition about how to estimate these probabilities or error bars, and people applied different methods to estimate them, and it's a non-trivial problem if you really want to check how well your estimates work in practice. So if you don't just hand wave and say, I have these estimates, these are the probabilities. Yeah. Any further questions? Yes?
Can you mention about the generalization properties? Is margin the only reason why?
The generalization properties of SVMs. So, well, I mean, one possible approach is you take this bound for the VC dimension, the upper bound for the VC dimension, you plug it into these general bounds that we had 2 days ago that were in terms of VC dimension, and then you will, with some caveats, but you will effectively, you will get something that qualitatively tells you about the generalization behavior of support vector machines. It's not the best possible bound, but it will tell you something about the trade-off between training error and margin maximization. So it's, you could say this is one way of motivating a support vector machine. Now there are more sophisticated bounds since then on that. They're not, sometimes they work for model selection, that you can choose parameters or things like kernel width using such a bound. But I think it's fair to say that in the end most people use something like cross-validation if they want to choose parameters and they want to be on the safe side. And that's even the case for many Bayesian approaches. So I used to have a postdoc in my lab, so maybe this I can tell this as an anecdote. A postdoc in my lab that Neil knows very well, but he's not listening now, who went to Microsoft and was working on some important problem there. He didn't have a permanent position yet, and he was trying very hard to do well on this problem, which also meant a lot of money for Microsoft. And I met him at some point and asked him, how did you do it? And he said he cannot tell the details, but I asked him, well, I just want to know, did you use cross-validation? And he said, oh, I wanted to win. So, so in the end, if it's important, most people use something like that. But still, of course, so the theoretical work is elegant and very interesting to understand what's going on. So it's more to get insight, but it's not so easy to change the way things are done in practice. Yes?
As far as I know, you have to specify the number of features in advance if you train an SVM. So is there any cool idea on how you can, during training, adaptively add new features? So for example, in an active learning scenario, when you observe new features, it might be important.
Well, okay, so you have to, for the recording, she says, and it's true, in the support vector machine you specify the number of features beforehand, because you specify the data that you're going to use in the kernel data. Now you could do something like, someone came to me after the session yesterday and said, well, how about multiple kernel learning? So there are some methods for support vector machines where you use a whole set of kernels. And you could, for instance, if you were interested in feature selection or in something like that, you could say, I'll define a number of kernels that some of them you look at all of the features, some of them only look at a subset, and then you can write down optimization problems where you're not only maximizing margin, but you're also maximizing something like the coefficients in front of each kernel. So you work with a convex combination of kernels, and you automatically optimize which one of them in the end is really the one that's used mainly, or maybe even exclusively. So you could do something like this. There are some other approaches also for feature selection. So if you start with a huge set of features and you want to somehow get to a subset of these features, various modifications of support vector machines, multiplicative update rules to put different amounts of weight on different features, but it's a sizable field by now. Yeah, so there are some approaches, but that's I don't think there's a final answer to this.
Actually, I didn't want to throw away features.
Yeah.
Feature selection you normally do, but I would like to generate new ones. For example, if you apply SVMs to text classifications,
Yeah.
you often observe new words in text data you cannot handle.
So you mean you have a new feature which you have observed only for some of the training points, or then do you have it for all training points?
I never observed it in training, only in testing, but I can't use it.
It's a new feature that you only observe in testing. Okay, it's an interesting question. Well, you know, I think I think it's maybe the first reaction could be that it is nonsense, but I don't think it is. It's potentially it's interesting. It might be related to this. So there's some recent work of Babnik, which he calls learning using privileged information, which is kind of related to what you're asking. So maybe you you can look at these papers. There's one or two papers on that. That's kind of interesting, yeah. Yes?
The biggest problem is probably that of zero-shot learning, where you have classes for which you've never seen exemplars before.
Zero-shot learning?
I mean, in, for example, massively multi-label classification, where labels run into millions. You might not have enough training data for even. So there is some work on zero-shot learning. Like to
Yeah. I mean, I've heard about one-shot learning before. I've never heard about zero-shot learning. But so it sounds hard, but maybe. Yeah, no, I agree. These are interesting problems. So that's related to the other question, yeah. And in practice, probably this happens a lot, that you don't know a priori which kind of features you're going to see. So I'm not aware of any beautiful theory that explains how to best do this. Of course, one can think of all sorts of hacks. You could think of learning additional models that take into account the new features, and then somehow combining the new models with the old ones and stuff like that. But then it becomes a lot of tuning and engineering. Yeah. Yes?
So do we train the support vector machine the primal optimization problem, or like under what conditions?
There are some training methods that train SVMs in the Primal, yeah.
So
It's like something called the Lagrangian SVM, which I think is training in the Primal by Mangasarian, and some other approaches as well. So it's a whole, SVM training is a whole industry now.
Olivier has few.
Olivier Chapelle has also some training methods in the Primal, yeah. I guess it also depends a bit whether you are dealing with linear kernels or with nonlinear kernels. For linear kernels, it's probably a little bit harder to train the Primal, but for linear kernels, it's sometimes more efficient to work directly with the weight vector rather than working with a huge expansion of the weight vector in terms of support vectors. But I have to say I'm sort of I was interested in support vector optimization at the beginning of that field, but now this has become a very specialized field, and I'm not following the details of the optimization methods anymore. I mean, it's become quite sophisticated, which is good for our field. I guess we're getting more mature, and which is good for those people that are specifically interested in optimization. And I think, I mean, in the end, it's all a matter of taste what we work on. So in terms of objective criteria, I think large-scale learning is maybe one of the most important topics nowadays, because we have huge data sets. So if you are very much interested in this kind of stuff, optimization, tricks for doing large-scale problems, it's a good topic to work on. Any last questions? If not, I would thank you very much, and I think I'll see you around.